We saw in the last lecture that holomorphic functions can be identified with complex analytic functions. Basically, given the point z0 in the domain of definition omega of f, we have small disks such that its closure is contained in omega, and where the function f can be written down as a power series. The power series converges in this disk to our given function f. We already saw as a consequence of this that if f is holomorphic, so is f prime, and that if f is holomorphic, and it turns out that f is infinitely differentiable. All these are consequences which we immediately drew from this theorem. We will now look at one more corollary to this theorem. It's called the Factor Theorem for analytic functions. Analytic functions, or rather complex analytic functions, and holomorphic functions are the same. Now I will start using them interchangeably, and yeah, there is no necessary distinction to be made between these two. Okay, let f be, so let omega be open subset of the complex plane, and f from omega to c be a complex analytic function, be a holomorphic function or a complex analytic function. Let me use the term complex analytic a couple of times so that we get used to it, such that f of z0 is equal to 0. It vanishes at a point z0 in omega. Then there exists a unique complex analytic function. So I'll slowly stop writing complex analytic and just write analytic functions like I wrote here. There exists a unique analytic function g from omega to c such that f of z is equal to z minus z0 times g of z. Just like how we can do for polynomials, we can do something similar for holomorphic functions as well. And it's actually factoring out the linear term z minus z0. Let's give a proof of this. The proof is going to use the theorem which helped us identify complex analytic functions and holomorphic functions. Okay, the first thing to note is that away from z0, we don't have much work to do. For on omega minus the point z0, 1 by z minus z0 is a holomorphic function, is holomorphic, and clearly, and defining g of z to be equal to f of z by z minus z0 is holomorphic on omega minus z0, and by very definition this g satisfies the required conditions. But the problem starts arising when we start focusing at the point z0. That is where we do not have 1 by z minus z0 defined, and in fact we are looking at 1 by z minus z0 times f of z, but we still will be able to redeem ourselves by using the fact that in a neighborhood of z0 f has a power series expansion. We write that down. Since f is complex analytic, what did we prove earlier? We proved that if R is such that dz0R closure is contained in omega, then f of z has a power series expansion in dz0R. So let's do let's consider one such power series expansion. Of course, the power series expansion, it's going to be unique, and write down the terms of the power series. In dz0R, which is contained, where dz0R is bar is contained in omega, we have the following power series expansion. f of z is equal to summation a n z minus z0 to the power n, where n goes from, let me be careful, it's not going to be from 0 to infinity here, it's going to be from 1 to infinity, because f of z0, which is a0, is equal to 0. So in particular, we will be able to write this as z. So for z in dz0r, in the disk of convergence of this power series, if you look at, define g of z to be equal to summation a n plus 1 z minus z0 to the power n, where n goes from 0 to infinity. And it's a good check for you to sit down and work out that g converges in dz0r as well. It has the same radius of convergence as the power series summation a n z minus z0 to the power n. And on dz0r, we have z minus z0 times g of z is equal to summation a n plus 1 into z minus z0 to the power n times z minus z0, which is equal to summation a n z minus z0 to the power n, where n is going from 1 to infinity, which is equal to f of z. This is in particular satisfied at the point z0 as well, because f of z0 is equal to 0 and the left hand side is equal to 0 as well. So what do we have? Hence, on dz0r, we have f of z is equal to z minus z0 times g of z. Now interestingly, we already have defined g of z in the intersection dz0r minus z0 intersected with omega. We know that this is equal to f of z by z minus z0, and one can sit down and check that on dz0r minus the point z0, g of z coincides with f of z by z minus z0, by considering the fact that that's the disk of convergence of f. That g is complex analytic follows from the fact that f by z minus z0 is holomorphic on omega minus z0 and therefore is complex analytic, and at z0 we have given an explicit expression for g in a neighborhood of z0. So it's complex analytic at every point in omega, and further uniqueness of g. So let me just note that down. G is complex analytic at every point in omega minus z0, since f by z minus z0 is complex analytic. G has a power series expansion around z0 by definition. We are done. The uniqueness of the function g follows by the fact that g is continuous at the point z0. At other places anyway, f by z minus z0 makes sense. Uniqueness follows by continuity of summation a n plus 1 z minus z0 to the power n at z0. And with that, we have a factorization of f of z into z minus z0 times g of z. Let's prove one more consequence. This consequence is classically called as the principle of analytic continuation. It says that if we have two holomorphic functions which agree on an open subset or a disk contained in the domain omega where both these functions are defined, then both f and g should be equal on omega necessarily. Let me write that down. This is called the principle of analytic continuation. Let omega be some open connected subset of C. We were not imposing this condition of connectedness in the previous corollaries till now, but right now let's put this condition as well. Omega be an open connected subset of C, and consider f and g two functions, and f comma g from omega to C be complex analytic or holomorphic on omega. Suppose f and g agree on a non-empty open subset of omega. On a non-empty open subset. Then f is identically equal to g on omega. The principle of analytic continuation tells us something very substantial. So, for example, if omega was the entire complex plane, that means that f and g would be entire functions. Now, if f and g agree on a small neighborhood of 0, let's look at say a disk of radius half around 0, and suppose f and g agree on a disk of radius half around 0, that forces f to be equal to g on the entire complex plane. Some sense of rigidity always is associated by the imposition of holomorphicity on f. Let us give a proof of this statement. The key fact is to use the connectedness of our domain omega. The fact that omega is open connected is going to be used crucially. And how do we do that? Define the set E to be the set of all those points z in omega such that the derivatives at the point z and the derivatives of f at the point z coincides with the derivatives of the function g at the point z. So, this is the set of all z's is that fn of z is equal to gn of z for all n in natural numbers. So, if you notice, the hypothesis tells us that f and g agree on a non-empty open set, and therefore, the set E is non-empty. E is non-empty since f and g agree on an open subset of omega. The non-emptiness is covered. The first claim is that we shall prove that E is closed. That is again easy because if you look at En be the set of all those points in omega such that fn of z is equal to gn of z for a fixed n. Now, we have already proved that if f is holomorphic, then f prime is holomorphic, in particular it is continuously differentiable, in particular it is smooth, and therefore the nth derivative of f is a continuous function. Similarly, the nth derivative of g is also a continuous function, and therefore the set En where fn and gn are equal, that set is going to be a closed set. Since fn and gn are continuous, En is a closed set. It is just the pullback of 0 under fn minus gn. And further, we have E is equal to the intersection of En, which is an arbitrary intersection of closed sets, which is closed. Therefore, E is closed follows very easily. The only thing to check is that we shall see that E is open. And to do that, let Z0 be some point in E. That implies that Fn at Z0 is equal to Gn at Z0. This would imply that in the power series expansion of F around Z0, the nth coefficient, which is captured by Fn by n factorial, that is the same as Gn by n factorial, which is the nth coefficient of the power series expansion of G around Z0. So, this implies that F and G have the same power series expansion. This is for all n in natural numbers. That's what forces the power series expansion to coincide in dz0 r, where dz0 r bar is contained in omega. The moment we have that, this implies that Fn of w is equal to Gn of w for all n in natural numbers, and dz0r is contained in E, which implies that E is open as well. And by connectedness, this will be a separation if E is not the entire set. Since omega is connected and E is non-empty, we have E is equal to omega, and that is precisely what we had set out to prove. Notice that if E is equal to omega, that would mean that F is equal to G on the entire set omega. Let us look at a slightly stronger version of this statement. We can actually prove that the 0 set of a holomorphic function will always be isolated. In some sense, we are proving a stronger version of what we have just proved. We are just proving that the set of points at which f and g, two functions defined on omega, the set of points where f and g agree, that shouldn't have a limit point. That is what we will be proving. It is not just on an open set that we need. The moment f and g agree on a set which has a limit point, we will be able to show that f is identically equal to g. This theorem is also sometimes called as the identity theorem. So, non-trivial holomorphic functions have isolated zeros. Let me write it down, and then we will see what the exact statement is. Let omega be an open connected subset of C. And f from omega to C be a holomorphic function, or a complex analytic function if you prefer it that way now, which, so let me add a non-trivial holomorphic analytic function, okay, which is not identically equal to 0 that means there is at least one point where our function f is not 0, and such that f of z0 is equal to 0. Then there exists epsilon positive such that f of z is not equal to 0 on dz0 epsilon minus z0. So, at any point in the disk, in the punctured disk of radius epsilon around z0, f will not vanish. That is what it means to say that the zeros are isolated. The moment we have a 0, we will have a disk such that in disk around the 0, such that in the punctured disk f does not vanish at all. Let us give a proof of this statement. The first observation is that at the point z0, all derivatives will not vanish. So, that is the first observation. Since f is not identically equal to 0, let me put it this way. If fn of z0 is equal to 0 for all n in natural numbers, that would just mean that the power series expansion of f in a neighborhood of z0 will have all coefficients equal to 0, and therefore in that neighborhood it would be equal to the 0 function. But by the principle of analytic continuation, then f should be identically equal to 0 on the entire complex plane, in the entire domain omega, open connected set omega. But we have already assumed that f is not identically equal to 0, and therefore this cannot happen. So let me just note that if fn of z0 is equal to 0 for all n, this would imply that f is identically equal to 0 on omega by using the principle of analytic continuation, which is a contradiction. Hence, there exists n or maybe n naught such that f n naught of z naught is not equal to 0, or maybe we can pick n naught to be the smallest such n. So let me just reword it. Since f is not identically equal to 0, there exists some n. Let n naught be the smallest positive integer such that fn naught of z naught is not equal to 0. Notice that n naught is greater than or equal to 1, because if you look at f0 of 0, that's just f of 0, and we know that that is equal to 0. So n naught should certainly be greater than or equal to 1. Since for every k less than n naught, fk of z naught is equal to 0, we can apply the factor theorem which we proved in the initial part of this lecture repeatedly, iteratively, to conclude that you can write f as z minus z0 to the power n naught times g of z. Let me just write that down. Since fk of z0 is equal to 0 for all k less than n naught, by applying the factor theorem, the factorization theorem rather, of analytic functions, notice that f is holomorphic, in particular its complex analytic. We have f of z is equal to z minus z0 to the power n naught times some function g of z. Now, the key thing is to apply factorization theorem to f of z, write it as z minus z0 times g0. Now, you look at the derivative will tell us that g0 of z0 is also equal to 0 if n naught is greater than 1. And then write g0 of z as z minus z0 times g1 of z, and therefore we will be able to write f as z minus z0 to the power 2 times g1 of z. This is being done iteratively. We have g of z in this manner. But then if g of z naught were equal to 0, that would imply that f n naught of z naught is also equal to 0. But we have assumed that n naught is the smallest integer where this does not happen, where fn of this is a contradiction, where fn of n naught of z naught is not equal to 0. That's something which we have assumed, and therefore this implies that g of z naught is not equal to 0. But g is again going to be power series, and therefore it's holomorphic, and because of that we will be able to conclude by the continuity of g, by continuity of g, there exists some epsilon positive such that g of z is not equal to 0 on dz0 epsilon. Notice that z minus z0 to the power n does not vanish on d of z0 epsilon minus z0. The only 0 of z minus z0 to the power n is the point z0. So, on dz0 epsilon minus z0, this does not vanish. Hence, z minus z0 to the power n into g of z does not vanish on dz0 epsilon minus the point z0. This implies that f of z does not vanish on dz0 epsilon minus the point z0. Notice that this is a very powerful result in the sense that we don't now demand that f and g are coinciding in an open set. We just need to show that if f and g coincide on a set which has a limit point, then f minus g will be vanishing at a set which has a limit point, and at the point where at the limit point the 0 is not going to be isolated, which would contradict our theorem which we have just proven, and hence f should be identically equal to g. So this is slightly stronger than the principle of analytic continuation. Some of its consequences are remarkable. So for example, consider the function f of x equal to sine square, rather f of z equal to sine square z plus cos square z. If we know that sine z and cos z extend the sine function and cos function which are defined on the real line, we know that sine square x plus cos square x is equal to 1 on R. Now R is certainly one set which is having limit points. In other words, this forces sine square z plus cos square z to be equal to 1. So we don't even have to worry looking at the power series expansion to conclude this particular identity about sine and cosine. Of course, we have already done this by looking at the explicit power series expansion in the initial stages of this course, but this is one observation using the identity theorem, or the fact that non-trivial analytic functions have isolated zeros. So we will see that this theorem has some really beautiful applications when we look at some of the problems at the end of the week's lectures. Let's move ahead and prove a higher order version of the Cauchy integral formula which we have proved in the last lecture. So this is called the higher order Cauchy integral formula. We have already seen that holomorphic function is complex analytic, and not only did we conclude that it is complex analytic, we also concluded what the coefficients of the power series expansion at any point z0 is going to be. Let me note that down and use it to conclude what the nth derivative at the point z0 will be. Let f from omega to c be holomorphic or complex analytic on an open set omega in C, and z0 be a point in omega with dz0 r bar contained in omega. Let gamma be a curve, just like in the Cauchy integral formula. Let gamma be a curve in omega minus z0, homotopic as closed curves. So this is a closed curve, by the way. Otherwise, we cannot talk about homotopic as closed curves. Homotopic as closed curves to reparameterization of gamma 1, where gamma 1 of t is equal to z0 plus r e to the power it, where t belongs to 0 to 2 pi. So this is going to be where in omega minus z0. Oh, I have already written that. In omega minus z0 has already been captured here. So in omega minus z0, we have gamma is homotopic to the circle of radius r around z0. Then Fn at z0 is going to be equal to n factorial by 2 pi I times the integral f of z by z minus z0 to the power n plus 1 dz. The proof is actually already taken care of. Let me just note down the steps involved since F is complex analytic. At Z naught and the coefficient an in the power series of f, in the power series expansion of f, is given by, this is given by an is equal to 1 by 2 pi I times the integral over gamma 1. Oh, this is over gamma, by the way. We'll come to it. This one is integral over gamma 1 f of z by z minus z0 to the power n plus 1 dz. Now, since gamma is homotopic in omega minus z naught to gamma 1, this is also in particular equal to n factorial by 2 pi I times the integral over gamma 1 of f of z by z minus z0 to the power n plus 1 dz. By Cauchy's theorem, we do have that. Since ans are the coefficients appearing in the power series expansion of f, we know from our knowledge of power series, which we developed in weeks 2 and 3, that the coefficients an can be written in terms of the nth derivative of f at the point z naught. We know that an is equal to fn at z naught by n factorial, and by plugging it in, we have fn at z naught is equal to n factorial by 2 pi I times the integral over gamma 1, which is the same as the integral over gamma of f of z by z minus z naught to the power n plus 1 dz. And this is what we had set out to prove. So, if you notice, when n is equal to 0, we just end up with our usual Cauchy integral formula. That is why this is also called as the higher order Cauchy integral formula. And as a consequence, we directly have the Cauchy estimates. Using the higher order Cauchy integral formula, we will also be able to place bounds on the derivatives of f in omega. Let's see what the exact statement is. Let omega be an open subset of C and F from omega to C be holomorphic. Suppose Z0 is some point in omega such that the disk of, say, radius r bar is contained in omega for some r positive. Let gamma of t be equal to z0 plus r e to the power it for t in 0 to 2 pi. Basically, it is the circle of radius small r around z naught. Suppose the absolute value of f of z is less than or equal to m for all z in gamma, in the image of gamma rather, gamma of 0 to 2 pi, then for all n in natural numbers, we will be able to put a bound on how the derivatives of f at z naught will behave. Like this is going to be less than or equal to m into n factorial by r to the power n. The proof is going to be quite straightforward. We just use the higher order Cauchy integral formula. Let me just write that down. By Cauchy integral formula, fn at the point z naught, this is going to be equal to 1 by 2 pi I times the integral over gamma of f of z by z minus z naught. So, there is an n factorial here which I missed, z minus z naught to the power n plus 1 dz. And by looking at the absolute value here, this is going to be the absolute value here, which is going to be n factorial by 2 pi times, which is less than or equal to the absolute value of this number minus the absolute value of the integral, which is bounded by m by r to the power n plus 1. That's precisely the bound of this quantity, times the arc length of gamma, which is 2 pi r. So by cancellations, we end up with which is equal to m into n factorial by r to the power n. So we'll see a few examples of how Cauchy's estimates can be used to conclude substantial conclusions on holomorphic functions in the problem session. Let me stop here.